In Embed2Scale, we aim to develop new methodologies in order to compress data, Earth observation data, efficiently.
Embed2Scale aims at providing compressed embeddings compared to sharing raw data. So if you look at nowadays world, AI is everywhere. And those AI algorithms, they don't use words. They work with embeddings. So that's their lingua franca. Basically, the data volumes are so large. If you want to do global assessments, it's not humans looking at the data of Earth observation and deciding where a climate risk happens or not. So we have to use algorithms. Accordingly, the language of algorithms should be used, and that's kind of what we are aiming at in the project.
We are providing access to the data, more or less. We want to democratize access to Earth observation data, hopefully through our Sentinel Hub services, but not necessarily. So our role in Embed2Scale is to facilitate harmonization and discoverability of the data, both the data that is needed as input to the embeddings themselves, and then later on the embeddings themselves. The challenges of Earth observation data are many, but one of them is definitely the amount of data that we have. In Embed2Scale, we're trying to drill down on that issue, maybe in particular. So how to make petabytes of data work across different data providers. So we know that going from one data center to another data center and transferring all that data comes at a price, literally. So what we want to do, or one of the things we want to do, is make this cost smaller by using embeddings. So condensing the data so that the transfer is smaller.
At the German Aerospace Center, we have a team that deals with these problems of combining the latest in AI with Earth observation data from satellites and of different modalities like images or radar information.
We are mainly pushing the boundaries of AI to make a difference for climate impacts and sustainability. Within the project, we are responsible to work on foundation models and neural compression to result in embeddings which can be efficiently distributed and be used by downstream applications to run climate assessment at scale.
We coordinated the use cases to have a sort of connection between the technical partners and the real use case scenarios.
The use case we'll be working on is really about weather and climate. And weather and climate has always been a very data-rich science. We occupied the biggest supercomputers early on before other people actually used them. And now we're at another revolution of weather and climate science where we build models that are extremely high resolution and extremely local and will be really important for impact assessment. But therefore they produce a ridiculous amount of data. And the same is true for satellite data. We have more satellite data than ever before. And therefore the case we're facing is we need to find ways to handle this data. And the case studies we'll be working on in Embed2Scale will exactly deal with some of these questions. How do we compress this data and make it therefore manageable to even store or transfer? But then also how to analyze the data in a more compact, optimized way. How do we learn new things from this compressed data that we couldn't otherwise learn so easily?
So biomass estimation is essentially the task of trying to estimate at any location on the planet the quantity of wood you have, to say roughly. And the problem with this task is that we know how to do it very efficiently, but for that you need to go on the ground, cut the tree, put them in an oven. Obviously this is not scalable, so people have worked on methods that you can do at a larger and larger scale without destroying the trees. But ideally what we would like to do is to do this from satellite imagery, which you can have really at a high resolution and very frequent refresh rate.
So I see the opportunities in that project mainly in bringing all of these AI methodologies to the test. Everyone claims the universe. We hear about foundation models nowadays. We hear about, oh, everything is superior in terms of AI. But in practice, that is not always the case. And this combination of our methodology being applied to real use cases helps us to understand where is the opportunities, but maybe also the limitations in terms of accuracy that we can achieve, or in terms of how well these methodologies can compress in compared to standard algorithms like JPEG 2000, etc.
So this project will unlock certain aspects of Earth observation and weather research, because at the moment we have the data gravity problem. We cannot transfer all the data and bring it all to one place. And with this project, this will be possible. It will save us a lot of energy, because a lot of the pre-computation is only happening once, and all the downstream projects can benefit from it.
The findings from this project will have the potential to really transform our way to store the data these models generate, and also the Earth observations generate, and therefore really make it possible to actually do science that we couldn't otherwise do. It also will allow people in the global south to participate, because some of these data sets are too big to transfer and to analyze in locations where the computer resources aren't as big as in some of the global north. And therefore really it's a big possibility to transform the way we do weather and climate data.
This will enable to perform global assessments much faster and much cheaper by reducing the data to be transferred, by reducing the compute needed at the customer side, and by making data searchable and findable.